All right, we're in the home stretch here talking about CFD. And we're going to finish with this Reynolds average Navier-Stokes, or RANS. So we saw last time that it's just not going to be practical to do DNS simulations all the time. So we need some way forward, and so Reynolds averaging is the way forward. So we're going to talk quickly about how to develop Reynolds average Navier-Stokes equations, and then discuss solution techniques to do that with regard to CFD, some of the averaging schemes. We're going to talk about when we average, we develop this thing called the Reynolds stress, so how to solve what the Reynolds stress is and the closure problem associated with the Reynolds stress. And then I'll end with some models of the Reynolds stress tensor and some examples. All right, so we talked about in previous slides this idea of the energy cascade, and that the flows are self-similar, and so we can see this. This is flows in a wind tunnel, and this is flow taken from space. This is a cloud bank going over an island in the Pacific Ocean, generating turbulent flow field behind the island. It's kind of the von Karman vortex street, and this is the same flow behind the circular cylinder, albeit laminar. It's still self-similar to scales. So that's the idea of the turbulent length scales and the energy cascade. And you know that that's the case when you look at some movies or you see flows, and as I was talking about before, your brain naturally recognizes what seems real and fake. So I thought it's always fun to look at fake flows and see what they look like. You just look at the ones that are fake, because they're superimposing, trying to get you to believe that scales. So it's a small plus see these flows, we recognize as fake because our brain knows what the right Kolmogorov length scale distribution is. That's my theory anyway. All right, here's some real flows. This is that's the eruption of an Icelandic volcano, and you can see all of those beautiful scales. You know, you can see like big scale structure, like there's something big there, or maybe this, like this piece of cauliflower. And then you can see like kind of scales on that size, right? And then within that, you can see smaller ones, and within that, you can see smaller, and it goes right on down the scale lengths. They're really quite cool. Same with a flow field like this, like some giant waterfall or something. That's why I love to look at nuclear explosions. I could look at them all day on YouTube, just this cascade of scales. It's gorgeous to look at. All right, so the approach is going to be like this. As we saw last time, if we want to resolve those scales, we're going to have to have a grid whose delta x is on the size of the Kolmogorov length scale, and then we saw that the requirement then for a computational domain is 10 times the Reynolds number, going like e to the fourth, and then if we cube that, it gets even bigger. So the way forward here is to go back to our Reynolds decomposition, where we're going to take this fluctuating flow and we're going to average it to get an average flow field, and then the deviations from the average are this u prime, the fluctuating velocity. So the Reynolds decomposition says that the turbulent flow can be resolved into an average mean flow plus a fluctuating component. Now, if I time average this, if I just integrate the fluctuations over time, we're assuming that on average that'll be 0, right? So if I integrate this with respect to time, that'll be 0. And the integration of u, the turbulent flow field with respect to time, will just be this flat line, or give you back the average u bar. So again, I find this crazy because this is an idea that was put forth 100 years ago and still what we're using today. Likewise, we could do this for any component, temperature or pressure. We can break it into an average and a fluctuating component. So this pressure should have a little bar over it to mean average pressure. Okay. these are the metrics that we used, and we have a whole series of averaging rules, like the average of an average is still the average, or the average of a sum is the sum of the averages, or the average of a dot product is the averages of the dot product, or the dot product of the averages. So take a look at these various scaling rules, averaging rules, and here's a few more that you might need if you want to try out doing this yourself. So let's apply this average to something like the continuity equation. So this is the incompressible form of the continuity equation. Del dot U is equal to 0. So if I insert my Reynolds decomposition, it's del dot U average plus V average. And if I FOIL that, it really says that del dot, or the compressibility of the average plus the compressibility of the fluctuation, must be equal to 0. So since the mean flow must satisfy continuity, that says then that the fluctuating flow must also satisfy continuity. So that is the Reynolds decomposition of the continuity equation. It's the first step towards developing a Reynolds average Navier-Stokes formulation. If we wanted to do this to momentum, that's a little bit more complicated. That looks like momentum in the U direction, right, or in the X direction. So I'd have to insert my Reynolds decomposition for every term, and I'd have to expand it all out, and then I'd have to apply my averaging rules that I showed you on the previous page. And I think I'll leave it to you to go through that math. It is well worth trying it out. Nice cup of coffee. Not so easy to do. It's a two-bean level of difficulty. The key is to collect all the average terms and then recognize which one of those will cancel, and then see what's left over for the fluctuations. If you do that, this is what you'll get. Here is the average terms, and the fluctuations appear here, which is pretty interesting. So they look like a gradient of some new cross product, U prime average, U prime V prime average, U prime W prime average. So we call this a Reynolds stress because it's kind of the same form of this shear stress. So I've written it here more compactly, or in IGA coordinates. Here's our regular old shear stress term, which is a gradient or a diffusion-based term. And this also looks like it's a gradient or a diffusion-based term. It's del operating, or partial operating on this Reynolds stress, partial X, partial Y, partial Z. So what is this new thing, and how do we get it? It's definitely nonlinear, and it's complicated. It represents the multiplication of the fluctuations in each direction. It's called the closure problem. Essentially, I've generated a new dependent variable. So I need another set of equations, some sort of closure equation, so that I can close my set, right? If I have a new independent variable, then I have to have a new governing equation. So how to find out this closure problem? Let's see. Well, one guy that had a go at it was Boysenesque. You may remember Boysenesque from the past. He looked at it like, well, why don't we just, because it's kind of this form, why don't we put it in the same form as our regular old shear stress? So this is some sort of new turbulent viscosity, right? And the question is how to get this turbulent viscosity. If we're going to relate the Reynolds stress, this guy here, to the mean stress, which is what Boysenesque suggested, then we've generated just a new parameter, this eddy viscosity. This is the closure problem, or the mystery of the quotient. You know, that's from Led Zeppelin. I'm not sure if you're familiar with that. And I'm sure that's what they were talking about in the Rain song when they mentioned the mystery of the quotient, was the turbulent closure problem. So Boysenesque said, well, let's just relate it to the mean flow like this. Let's call this that each term within the turbulent eddy stress tensor is related to the gradient of the mean velocity, which we know. That's the off-diagonal terms and the diagonal term, times some new eddy viscosity. So really, ultimately, you can think of it as just turning up the viscosity. That turbulence, what it does is essentially increase our viscosity. A very simple sort of idea, but legitimate, crummy, but totally legit. Prandtl had his own suggestion. He kind of used the same idea from Boys and S, but said, well, it's really a mixing length. And so this new viscosity, this turbulent eddy viscosity, is related maybe to the gradient or to the mean gradient of the free stream flow times some whatever this length scale is, which is known as the Prandtl length scale. So we just pick some length scale in there to represent this new eddy viscosity. I mean, it's legit in the sense that that's the same way we think about modeling molecular interactions up to a continuum to approximate the viscosity of a fluid. Now, more modern sort of techniques are the K-epsilon turbulent model, which is really championed by Lander and Lumley. And so Lumley, I didn't realize he was dead, but I guess he just died. And they said, well, really what we should be doing is trying to come up with an evolution equation for K, this kinetic energy at the large scale, and the dissipation rate, because that's more physical as to what we think of as our model, and it connects us to the energy cascade. So they went round and round. I'm not going to give the derivation of this, but they came up with a model, as you can see here, that relates these two, so they're interdependent. There's epsilon appearing in the K equation, the K evolution equation. It evolves in time and in space. And here's epsilon, the dissipation rate, evolving in time and space. And it's equal to some cross terms here. And there's some coefficients. There are 1, 2, 3, 4, 5 of these coefficients, these closure coefficients. There they are. And so they fit these coefficients to data. So they just went into the flat plate and to the wake and to all of the bluff body flows, and they fit these coefficients, and they got this right here. So if you were to go to a CFD code and you were to click on turbulence, you would then get a model. Which model do you want to pick, the length scale model or whatnot? Most people click on the K epsilon model, and then it would show these parameters, like, do you want to accept these? You'd be like, I guess so, click, because what else are you going to pick, right? And then you'd be off and running. You'd be like, hey, I'm running a turbulence model. But are these the right ones? These are really, they come from no pressure gradients, no separation. This whole thing goes out the window if there's separation. But maybe you should have a look at these numbers and pick better numbers for your particular flow field, heat transfer and separation and so forth. So it's complicated, right, this closure problem. There's another way forward, and that is kind of in between doing DNS and doing Reynolds average, there's this large eddy simulation. And what that does is say, okay, look, maybe I can't resolve all the way down to the Kolmogorov length scale. Maybe I should just stop somewhere. And the justification is, well, if the flow is self-similar, if the turbulence is self-similar below some threshold, why don't I just use this model to represent the subscale turbulence? So what I can't model, what I can't resolve in a turbulent simulation because my grid is too big to resolve these tiny little eddies, I'll just assume that it's filled in with this self-similar model. So you just assume the shape of the distribution thereafter, and this is called the large eddy simulation. So you're really simulating the large eddies, and then you're connecting it to the energy cascade and then down into the viscous region in order to get the energy out of the flow legitimately. So it's kind of like, think of RANS as representing the large scale simulations, DNS really representing capturing all of the turbulent scales, but it's too hard to do that for all engineering problems. And LES kind of making the bridge there. Maybe that'll be the way forward really in the next 10, 20 years, is more and more LES type simulations. But in general, you can think of it, well, if this is the real flow in blue that we would get from a DNS simulation, RANS is just going to give us the average. There's not going to be any fluctuations in a RANS simulation. And LES will give us some of the fluctuations, maybe some of the large-scale fluctuations like you're showing here in red, but not the small-scale fluctuations associated with the smallest of eddies near the Kolmogorov length scale. So if I were to model some beautiful flow field like this, where you've got all of the richness of turbulence and the distribution of scales from the largest scale here to the smallest scale that you can't even see in the photograph. If I did that with a large eddy simulation, or sorry, with a RANS simulation, it would really look like this. This is what I'd get. I'd get the large scale, but all the small scales would be like blurred out, basically, because we're averaging those. I mean, your mesh is like this big, right? So if your computational mesh is this large, there's just no way to resolve the small, tiny little scales that are in there. Here's a comparison of what size effects do. This is a simulation. You can see here, this is a simulation where they're using adaptive mesh refinement. So where things are interesting, where the gradients are large, they're clustering cells on the fly. This is kind of a new technique. And so you're adding resolution where you need it. It's still a RANS simulation, but you get a little bit better temporal resolution as a result. So this upper one here, they added some grid cells. They were able to resolve it a little bit finer, but not enough. So what happens is you don't get the shedding and the temporal changes that you see because you didn't have the resolution to resolve it. Just like we saw with the lid-driven cavity flow. We didn't have cells small enough to resolve those secondary flows in the corner, so we never saw them, right? Still a legitimate solution, it just converged on the wrong solution. All right, that's the effects of RANS. Here's another one, comparing RANS to LES. This is using OpenFOAM. So again, you can see the LES is giving you small scale behavior, giving you the fluctuations, where the RANS is kind of averaging it all out. And 90–95% of what's done in industry is RANS. I wanted to show you one more simulation, and this is a really nice DNS simulation, a flow over an airfoil section. And now that you've seen a lot of this terminology, a lot of what's shown in this video should make sense to you. If you want to see more of these videos, click on this link below. Go to Google and type in Gallery of Fluid Motion. It'll take you to the APS website, and there you can find a lot of really high quality flow visualization and simulation work. So take a look at this. It is impressive. Look what they're resolving their mesh to. Got a lot of clustered cells there. So if the chord length is the imposed length scale, maybe they're about 8 or 6 times longer than the chord, the total domain length. 36 million core hours. So depending on how many cores they had at their disposal, give you an idea how long the simulation took. So they're tripping the flow to make it turbulent. So they got laminar inflow, and then they trip it to cause it to be turbulent. Look at that beautiful turbulent flow structure. That's insane. Those little hoops, those loops that you see are called horseshoe vortices or turbulent spots. That is really gorgeous. Little flow separation there in the mixing layer. So pretty cool, state-of-the-art stuff, but not necessarily useful for industry applications. So that's just some basic overview of CFD and its applications to laminar flows and turbulent flows and the challenges moving forward, eventually leading to the formation of the closure problem and turbulence, and then some solutions for the closure problem. I hope you enjoyed this module. And the closure problem, right? It is the last great problem in physics, or so some people think. So I hope you enjoyed this lecture. And, you know, speaking of the mystery of the quotient or the closure problem, I'm sure you've all heard Led Zeppelin's song, the Rain song, which is specifically talking about the turbulent closure problem. So I thought it might be appropriate to end this lecture with listening for Led Zeppelin's take on the mystery of the quotient. See if you can find where they actually mention this in the song. Bye.
It is the springtime of my loving, the second season I'm to know. You are the sunlight in my growing, so little warm I felt before. It isn't hard to feel me glowing. I watched the fire that grew so low. summer of my smile. Flee from me, keepers of the bloom. Speak to me only with your eyes. It is to you I give this tune. It isn't hard to recognize home. These things are clear to all from time to time. Oh, yeah. Oh, yeah. These are the seasons of emotion, and like the wind, they rise and fall. This is a wonder of devotion. I see the torch we all must hold. This is a mystery